General real-valued random variables. Okay, so we've looked at discrete random variables. We've also looked at continuous random variables. Is there some way we can mix the two? Well, sure. Think about this. What if each day you use some amount of water? Okay, water we think of as a fluid, right? Because it is a fluid. We might think of the amount of water you use every day as a continuous random variable, right? That makes sense. You might use 2 gallons or 10 gallons or 10.2 gallons or 10.222 gallons or 10.192234 gallons, etc. Or you could use exactly 0 gallons. Think about that, right? So in this case, the amount of water you use in a day is sort of a mixture between discrete and continuous. That's where we're headed with this. So let's review some properties of cumulative distribution functions. Properties of cumulative distribution functions. First of all, they're monotone, non-decreasing. Okay, they go up is what that means. Second of all, they're right continuous with left limits, meaning, well, they're continuous from the right. If you move from the right along the function, the limit there is exactly equal to the function evaluated at that point. Okay, they have left-hand limits, meaning that as you approach, as you approach from the left, the limit exists there, but it's not necessarily equal to the CDF evaluated at that point. Finally, the limit of the CDF as x goes down to negative infinity, 0 is, and then the limit as x goes up to infinity, the CDF is 100%. For example, let's take a look at CDF in the discrete case. Okay, so this is the discrete case. Always be very discrete with your cases. All right, this is the discrete case. Might have something that looks like this, right? Maybe do like that, and then I go like this, and then like that. All right, and then I'll go like this, and then like that. Maybe like that. Okay, and then maybe like this. Okay, and then on and on, right? Okay, and I'll drop a line like this, and I'm going to put a 1 right there. All right, this is a cumulative distribution function. It satisfies these 3 properties, right? It's monotone, non-decreasing. Okay, it's non-decreasing. It's basically going up. It never decreases. It sort of planes off, but it never decreases. It's right continuous at every point. Okay, even here, if I look here, say maybe I'll label these like this. Okay, even at A2, this CDF evaluated at A2 is equal to the limit of the CDF as x goes down to A2 from the right. Okay, so, and we indicate that that right continuity there with the closed dot. We indicate the left-hand limits property there this way, right? I can approach from the left. It certainly has the limit there, but the limit as I approach from the left is not actually equal to the function, to the CDF evaluated at A2. All right. Finally, of course, as x goes down to negative infinity, the CDF approaches 0. As x goes up to infinity, it approaches 1. These are the only 3 properties that CDFs must satisfy. They're the only 3 properties that CDFs have to satisfy. By the way, what is? How do we read this off? How can we make use of this? Well, this much right here, this is the probability that our random variable, I'll call it x, that our random variable equals the value A2. And this, guess what? This is the probability that our random variable equals A3. Okay? And this, guess what? This is the chance that x equals A1. Okay? So the size of the jump is the probability. Okay? The size of the jump is the probability. If I put a mark here and I call it smiley face, okay, then the probability that x is less than or equal to smiley face is just it's this much, right? It's this much. It's just the sum of these two jumps. It's the sum of all the jumps before it, right? That's because this is the cumulative distribution function. It accumulates all the probabilities up. All right, so what about in the continuous case? What about in the continuous case? OUS, continuous case. Well, continuous CDFs, or continuous random variables, have continuous CDFs, right? So maybe it looks something like this, and maybe here's my 1. Okay, in this case, you know, maybe here's A1, and I'll put A2 down there, A3 there. Okay, why not? But in this case, you know, maybe this is the CDF. Maybe this is the CDF of some other random variable. Okay, in this case, the probability that this random variable y equals A1 is clearly 0, right? It's 0 because, you know, it's really supposed to be the chance that it's less or equal to A1 minus the chance that it's strictly less than A1. Okay, so if you take the difference of those two integrals, you get 0. All right, but the probability that y is less or equal to A1 is indeed this integral, right, from negative infinity up to A1 of the density function f sub y of y dy. Okay, we already know that, but that's going to be in this case it's that mark, right? That's what this cumulative distribution function indicates, right? So, but there's sort of an in-between kind of case. What about something like this? What if I drew a picture that looks like this? Okay. Oops, let's make that flat. Okay. Now, what do you think about that? Is that a CDF? Yes, it satisfies all the known properties of CDFs. Okay. I don't know of any other properties, so we'll just go with these 3. It's monotone non-decreasing, isn't it? It's non-decreasing. It's going, well, here it's not increasing or decreasing, so it's not decreasing. Here it's increasing. Here it's, right? Okay, it's monotone non-decreasing. It's also right continuous with left limits everywhere, even at the jump points. Okay? Because of the way that I've drawn the dark and open circles there. Also, the limit as you approach negative infinity is 0, and the limit as you approach positive infinity is still 1. So this is also a CDF. It sort of mixes continuousness with discreteness. Okay, what this says is that you know, it's basically a continuous random variable, except that we allow these atoms to take place, is what you can call these things. That is, the probability of this random variable. Maybe we'll call this I don't know. Call this random variable S. Okay, so that this is the CDF of the random variable S. Okay, and the probability that S is equal to A2 is actually greater than 0, and the probability that this random variable S is actually equal to A3 is also something greater than 0. Okay, because there are jumps there of those sizes, and they're not 0. Okay, so this goes there, and this one goes there. Okay, pretty neat, right? Yeah. So Now, in this case, so how do we write the CDF? I mean, how do we define this CDF? Well, it's still defined, whoops, not like that. It's CDF of S, in this case. This is the probability that S is less or equal to this number S. Okay? But I want to be able to use an integral or a summation or something, so it should be some kind of integral from negative infinity up to S. And it needs to be a function of little s, right? So this little s is that little s. And so actually the way I can express this is with something called a Stieltjes integral. Of x. Okay? So this is an example of a Stieltjes integral. S-T-I-E-L-T-J-E-S integral. Okay? What is this d big F sub s of x? So what this is doing, what this says to do, is to integrate against the CDF. Okay, that is so d f sub x of x is, you can think of it as f sub x of x, the density function, times dx, if x is continuous. If x is a continuous random variable, or if you're at a discrete part, df sub x of x is the probability that the random variable takes on the value of x if discrete. So in fact, guess what? You can actually write CDFs, and you can write out probabilities for discrete random variables as integrals. You don't need summation symbols. In this sense, you can express summations using integrals. Pretty neat, right? So if if I wanted to know, for example, the chance that this random variable called S takes a value that's less than or equal to A2, it's going to be this, right? It's this right here. This is the probability that S takes on a value that's less or equal to A2. It's this right there. You have to, right, all of this is sort of like integrating a density function, integrating a density function, integrating a density function, and then finally you add just this number here, which is the size of the jump. Now, what is this? This is the probability that S is strictly less than A2. Do you see that?